Welcome to Dynamic Planet, Oceanography. In this video we'll dive deep into the fascinating world of Earth's oceans, exploring both their physical and geological aspects. Oceanography is the scientific study of the ocean, covering everything from the movement of water and currents to the rocks and sediments on the ocean floor. This field helps us understand not only how the oceans work today, but also how they have shaped our planet's history. Whether you're a student preparing for a competition or just curious about the natural world, you'll discover how oceanographers use practical skills like reading maps and interpreting data, as well as theoretical concepts such as the Coriolis force and ocean-atmosphere interactions. Let's set sail on this journey to uncover the secrets of our dynamic planet. Oceanography can be divided into two main branches: physical and geological. Physical oceanography focuses on the ocean as a dynamic system, studying currents, waves, and the principles that govern their movement, such as conservation of mass and energy. Geological oceanography, on the other hand, examines the rocks and sediments found on the ocean floor and margins, seeking to understand how these features formed and what they reveal about Earth's history. By combining these perspectives, scientists gain a comprehensive view of the ocean's role in shaping our planet. Throughout this video, we'll see how both branches work together to explain phenomena like plate tectonics, ocean currents, and the formation of underwater landscapes. The heart of geological oceanography is the theory of plate tectonics. The Earth's outer shell, called the lithosphere, is divided into several large plates that float atop the semifluid mantle. These plates are constantly moving, interacting at their boundaries in different ways. The crust, which is the outermost layer, is solid and rigid, while the mantle beneath can flow slowly. The core, made mostly of iron and nickel, is divided into a liquid outer core and a solid inner core. Understanding these layers is crucial for grasping how the movement of tectonic plates shapes the ocean floor, creates mountains, and triggers earthquakes and volcanic activity. Tectonic plates interact in three main ways at their boundaries: convergent, divergent, and transform. At convergent boundaries, plates move toward each other, often resulting in one plate being forced beneath another. Divergent boundaries occur where plates move apart, creating new crust as magma rises to fill the gap. Transform boundaries are where plates slide past each other horizontally. Each type of boundary leads to different geological features and events, such as trenches, ridges, earthquakes, and volcanoes. Recognizing these boundaries is key to understanding the dynamic nature of our planet's surface, especially beneath the oceans. Divergent plate boundaries are where two tectonic plates move away from each other. This process is most commonly seen at mid-ocean ridges, such as the Mid-Atlantic Ridge. Here, rising convection currents in the mantle lift the lithosphere, creating a ridge and a deep fissure. Magma rises to fill the gap, solidifies, and forms new oceanic crust. This continuous process gradually expands ocean basins and can lead to the formation of new sea. Divergent boundaries are also associated with shallow earthquakes and volcanic activity, making them important features in the study of oceanography. Mid-Atlantic Ridge is a classic example of a divergent plate boundary. Unlike what many might think, the ridge isn't a pile of volcanic material, but rather a high area formed by the uplift from convection currents below. Magma rises, fills the fissure, and solidifies, attaching to the edges of the separating plates. Over time, this process creates new ocean floor and gradually widens the Atlantic Ocean. The Mid-Atlantic Ridge is also a site of frequent, though usually mild, earthquakes and volcanic activity, making it a dynamic and ever-changing feature of the seafloor. Divergent boundaries occur beneath thick continental plates. The process is a bit different. The continental plate is arched upwards and pulled thin by extensional forces, leading to the formation of rift valleys. These rifts are characterized by normal faults and sinking central blocks. Over time, rivers and lakes may fill the rift, and if the rift deepens below sea level, ocean water can flood in, eventually forming a new ocean basin. The East African Rift Valley is a prime example of a continental rift in its early stages, while the Red Sea shows a more advanced stage where the plates have fully separated. Convergent plate boundaries are where two plates move toward each other. Depending on the types of crust involved, oceanic or continental, different features form. When oceanic crust meets continental crust, the denser oceanic plate subducts beneath the continental plate, forming deep ocean trenches and volcanic arcs. When two oceanic plates converge, both may subduct, creating trenches and volcanic island arcs. When two continental plates collide, they push up to form massive mountain ranges like the Himalayas. These boundaries are also sites of intense earthquakes and volcanic activity. Transform boundaries are unique because plates slide past each other horizontally. Unlike convergent or divergent boundaries, no new crust is created or destroyed here. Many transform boundaries are found on the ocean floor, connecting segments of mid-ocean ridges. One of the most famous examples on land is California's San Andreas Fault. These boundaries are known for producing earthquakes, as the plates can become locked and then suddenly slip, releasing energy. Understanding transform boundaries helps explain the distribution of earthquakes across the globe. Continental margins mark the transition between continental and oceanic crust. Active margins are found at convergent plate boundaries, where subduction zones create narrow, tectonically active regions with less sediment. Passive margins, in contrast, are located within plates far from active boundaries. These regions are wider, experience less tectonic activity, and often accumulate thick layers of sediment. Understanding the differences between active and passive margins is important for interpreting ocean floor features and the distribution of marine life. Reefs are fascinating underwater structures formed primarily by coral. Charles Darwin first classified reefs into three main types: fringing, barrier, and atoll. Fringing reefs grow close to shorelines, while barrier reefs form further out, separated from land by a lagoon. Atoll reefs develop when an island sinks below sea level, leaving a ring of coral around a lagoon. Patch reefs, which don't fit Darwin's scheme, are isolated clumps of coral. Reefs are vital for marine biodiversity, providing habitat for countless species and protecting coastlines from erosion. Patch reefs are small, isolated coral formations that don't connect to larger reef systems. They can be circular or rhomboid in shape and are usually separated by sand or mud. Patch reefs are important because they provide unique habitats for marine organisms and contribute to the overall diversity of reef ecosystems. Unlike fringing or barrier reefs, patch reefs are scattered and can be found in various locations, often in shallow waters. Their presence highlights the complexity and variety of coral reef environments. Ocean currents are powerful forces that move water across the globe. Surface currents are primarily driven by wind, which is itself influenced by the sun's uneven heating of Earth. These currents follow predictable patterns. Cold currents flow along western coasts toward the equator, while warm currents travel along eastern coasts toward the poles. Famous examples include the California current cold and the Gulf Stream warm. These currents not only affect climate but also influence marine life and human activities along coastlines. Beneath the surface, a global system called the Great Ocean Conveyor or thermohaline circulation moves water around the world. This deep circulation is driven by differences in temperature and salinity. In the North Atlantic, cold, salty water sinks and flows southward, eventually looping through the world's oceans. This process is slow. Water can take over 1,000 years to complete the journey, but it's crucial for distributing heat, nutrients, and gases throughout the ocean. The conveyor helps regulate Earth's climate and supports marine life at all depths. Coriolis effect, caused by Earth's rotation, plays a major role in shaping ocean currents. In the northern hemisphere, moving water is deflected to the right, while in the southern hemisphere it's deflected to the left. This effect creates curved wind and current patterns, making the movement of air and water more complex. The Coriolis effect is essential for understanding phenomena like the Ekman spiral and the formation of large-scale ocean gyres. Without it, currents would flow in straight lines between the poles and the equator. Ekman spiral is a fascinating concept that explains how wind, friction, and the Coriolis effect interact to move ocean water. When wind blows across the ocean surface, it pushes the top layer of water, which then drags the layer beneath it, and so on. Each deeper layer moves more slowly and is deflected further by the Coriolis effect, creating a spiral pattern. The net result, called Ekman transport, is that the overall movement of water is about 90 degrees to the right of the wind in the northern hemisphere. This process is crucial for upwelling and downwelling along coastlines. Upwelling and downwelling are important processes in ocean circulation. Upwelling occurs when winds and currents move surface water away from an area, allowing deep, cold, nutrient-rich water to rise and replace it. This process supports some of the world's most productive fisheries, as seen off the coasts of California and Peru. Downwelling, on the other hand, happens when surface waters converge and are pushed downward, carrying oxygen into deeper layers but reducing nutrients at the surface. Both processes are vital for marine ecosystems and global nutrient cycles. Surface convergence happens when winds or currents push surface waters together, causing water to pile up and sink, a process called downwelling. This brings oxygen to deeper ocean layers but reduces surface productivity. Surface divergence is the opposite. Winds or currents pull surface waters apart, creating a gap that's filled by rising deep water or upwelling. Upwelling zones are rich in nutrients and support abundant marine life. These processes are especially important in the centers of ocean gyres and along western continental coasts. Eastern intensification describes how ocean currents on the western sides of ocean basins, like the Gulf Stream and Kuroshio current, are stronger, narrower, and faster than those on the eastern sides. This happens because the Coriolis effect and wind-driven circulation pile water up on the western side of basins, creating powerful poleward currents. These currents transport warm tropical water toward higher latitudes, moderating climate and influencing weather patterns. In contrast, eastern boundary currents are slower, broader, and colder, supporting rich fisheries. These are swirling currents of water that form when a larger ocean current separates a section of water from its main flow. These can be small whirlpools or massive features spanning hundreds of kilometers. Eddies play a crucial role in mixing ocean waters, bringing cold, nutrient-rich water to the surface and supporting marine ecosystems. Some eddies are so persistent that they're tracked and even named, much like hurricanes. Their swirling motion helps distribute nutrients and heat, making them vital for ocean health. Thermohaline circulation is the part of ocean circulation driven by differences in water density, which are caused by variations in temperature and salinity. Cold, salty water is denser and sinks, while warmer, fresher water rises. This process creates a global conveyor belt that moves water, heat, and nutrients around the world's oceans. Thermohaline circulation is essential for regulating Earth's climate and supporting marine life at all depths. It's sometimes called the meridional overturning circulation or the global conveyor belt. Gyres are large systems of rotating ocean currents, formed by the Coriolis effect and global wind patterns. There are 5 major ocean gyres: the North Atlantic, South Atlantic, North Pacific, South Pacific, and Indian Ocean gyres. These massive circulations help distribute heat and nutrients across the globe. Gyres also influence weather patterns and play a role in the accumulation of floating debris, such as the Great Pacific Garbage Patch. Understanding gyres is key to grasping the movement of water on a planetary scale. Coastal currents flow along the edges of continents and are influenced by wind, waves, and the shape of the coastline. Two main types are longshore currents and rip currents. Longshore currents move parallel to the shore, driven by waves hitting the coast at an angle. They transport sediment and can cause significant beach erosion. Rip currents, in contrast, are strong, narrow flows that move directly away from the shore, often forming near sandbars or piers. Both types of currents are important for coastal processes and safety. Longshore currents are generated by waves approaching the coastline at an angle. As waves break, they push water and sediment along the shore, creating a current that runs parallel to the beach. The strength of a longshore current depends on wave velocity, the angle of approach, and the slope of the beach. These currents can transport large amounts of sand, reshaping coastlines and impacting man-made structures. Understanding longshore currents is essential for managing beach erosion and coastal development. Currents are powerful, narrow channels of water that flow from the shore out to sea. They form when longshore currents encounter obstacles like sandbars or piers, causing water to funnel outwards. Rip currents can be dangerous for swimmers as they move quickly and can pull people away from the shore. However, they usually break up not far from the beach. Recognizing and understanding rip currents is important for beach safety and rescue operations. Welling is a process where deep, nutrient-rich water rises to the surface, often along coastlines where winds drive surface water offshore. This influx of nutrients supports the growth of phytoplankton, forming the base of the marine food web and leading to highly productive fisheries. Regions with strong upwelling, like the coasts of Peru and California, are known for their abundant fish populations. Upwelling is vital for both marine ecosystems and human economy. Waves are repeating disturbances that travel through water, transferring energy from one place to another. Key characteristics of waves include the crest, highest point, trough, lowest point, height, wavelength, amplitude, frequency, period, and speed. Waves are generated by wind, earthquakes, or other disturbances, and their properties determine how they move and interact with the shore. Understanding wave dynamics is essential for navigation, coastal engineering, and predicting natural hazards. Wave steepness is the ratio of wave height to wavelength. When this ratio exceeds 1:7, waves become unstable and break, forming breakers. Breakers can be plunging with a violent crest or spilling with a gentle white cap. The type of breaker depends on wave energy and the slope of the seafloor. Understanding wave steepness helps predict coastal erosion, surfing conditions, and the impact of storms on shoreline. Ocean waves come in many forms. Capillary waves are tiny, formed by wind and surface tension. Chop refers to small, rough waves, while ripples are short, wind-driven waves. Standing waves oscillate in place, created by waves reflecting off obstacles. Swell refers to long, smooth waves that travel far from their origin, often forming surf when they reach shore. Each type of wave has unique characteristics and plays a role in shaping the ocean's surface. Tides are the regular rise and fall of sea levels caused by the gravitational pull of the moon and sun. The moon's influence is stronger due to its proximity, leading to daily high and low tides. Tides play a crucial role in coastal ecosystems, navigation, and human activities. Understanding tidal patterns helps predict flooding, plan harbor operations, and manage marine resources. Spring tides occur when the sun and moon align, producing the strongest tidal effects. During these times, high tides are higher and low tides are lower than average. Neap tides happen when the sun and moon are at right angles, resulting in weaker tidal changes. Understanding the timing and strength of spring and neap tides is important for coastal planning, fishing, and recreational activities. El Niño and La Niña are major oceanographic phenomena that affect global weather patterns. El Niño occurs when trade winds weaken, allowing warm water to move eastward across the Pacific, disrupting normal upwelling and causing heavy rains in some regions and droughts in others. La Niña is the opposite, with stronger trade winds and cooler ocean temperatures in the eastern Pacific. These cycles impact fisheries, agriculture, and weather worldwide. El Niño brings wetter winters to places like Florida and drought to Indonesia and Australia. It can disrupt fisheries by replacing nutrient-rich cold water with warm, nutrient-poor water. La Niña, on the other hand, enhances Atlantic hurricane activity and brings cooler, drier conditions to the eastern Pacific. These events can have serious economic and environmental impacts, making their prediction and monitoring a priority for scientists. Ocean sediments come from various sources and are classified into four main types. Lithogenous or terrigenous sediments originate from land and are common near continental margins. Biogenous sediments are formed from the remains of marine organisms and are found in ocean basins. Hydrogenous sediments precipitate directly from seawater and are relatively rare. Cosmogenous sediments come from space, such as meteorites, and are the rarest. Each type of sediment tells a story about the ocean's history and processes. Oceanographers use a variety of tools to study the sea. The acoustic Doppler current profiler measures current speed and direction using sound waves. Nets like the Bushmaster and Chimneymaster collect deep-sea organisms. Cloud cards help measure water motion near the seafloor. Drifters track ocean currents, while satellites provide global data on ocean conditions. Other tools include sonar for mapping the seafloor, submersible collectors for fragile organisms, and trawls for sampling marine life. Each tool offers unique insights into the ocean's mysteries. Topographic maps are essential for interpreting ocean features. These maps use contour lines to represent elevation or depth. Each line connects points of equal elevation, and the spacing of lines indicates slope. Closer lines mean steeper slopes. Closed contours represent hills or depressions, while V-shaped lines indicate valleys or streams. By reading these maps, scientists can identify features like ridges, trenches, and seamounts, helping them understand the shape and structure of the ocean floor. Contour lines on a map never cross and always form closed loops. Moving from one line to another indicates a change in elevation, either uphill or downhill. The direction of the V-shape in contour lines crossing a stream points upstream. Evenly spaced lines mean a constant slope, while uneven spacing shows changing slopes. Mastering contour lines helps oceanographers and geologists visualize underwater landscapes and plan research expeditions. Once are boundaries between air masses of different densities. There are four main types: cold fronts, warm fronts, occluded fronts, and stationary fronts. Cold fronts bring thunderstorms and move quickly, while warm fronts bring steady rain and move more slowly. Occluded fronts occur when a cold front overtakes a warm front, and stationary fronts form when neither air mass can move the other. Understanding fronts is important for predicting weather at sea and on land. Precipitation includes all forms of water that fall from the atmosphere, such as rain, snow, and hail. At higher latitudes, snow and ice are common, while rain dominates near the equator. Precipitation is a major source of freshwater for the oceans and influences salinity, circulation, and marine life. Understanding precipitation patterns helps scientists predict changes in ocean conditions and their impacts on global climate. Atmospheric circulation drives the prevailing winds that influence ocean currents. At low latitudes, easterly trade winds blow from east to west, while westerlies dominate the middle latitudes. These wind patterns help create the major ocean gyres and drive surface currents. Understanding atmospheric circulation is essential for predicting weather, climate, and the movement of ocean water around the globe. Halocline is a layer in the ocean where salinity changes rapidly with depth, while the pycnocline is where density changes quickly. These layers are important for understanding ocean stratification, mixing, and the movement of water masses. They influence nutrient distribution, marine life, and the behavior of currents. Identifying the halocline and pycnocline helps scientists interpret oceanographic data and predict changes in the marine environment. Tidal resonance occurs when the natural period of oscillation of a body of water matches the period of tidal forcing, amplifying tidal ranges. This phenomenon can lead to exceptionally high tides in certain locations, such as the Bay of Fundy. Understanding tidal resonance is important for predicting extreme tidal events and managing coastal infrastructure. It's a fascinating example of how physical principles shape the ocean's behavior. Ocean observing tools range from simple devices like cloud cards to advanced technologies like satellites and sonar. Each tool is designed for specific tasks, such as measuring currents, mapping the seafloor, or monitoring water quality. Some tools work best in certain environments. For example, some can't operate efficiently on rocky bottoms. The development and use of these tools have revolutionized our understanding of the ocean, enabling real-time data collection and global monitoring. Being able to read and interpret maps is a vital skill for oceanographers. Maps help scientists identify features like ridges, trenches, and seamounts, plan research expeditions, and analyze data. Understanding contour lines, elevation changes, and map keys allows for accurate interpretation of underwater landscapes. These skills are not only useful in competitions, but are also essential for real-world scientific research and exploration. The ocean is a dynamic and complex system, shaped by geological forces, physical processes, and the interplay of wind, water, and life. From plate tectonics and ocean currents to waves, tides, and marine ecosystems, every aspect is interconnected. By studying oceanography, we gain insights into Earth's past, present, and future. Whether you're preparing for a competition or simply fascinated by the sea, understanding the ocean's dynamics is key to appreciating our planet's incredible diversity and resilience.